In this lecture, we're going to examine in a little bit greater detail the various principles of measurement and the different measurement scales that exist when conducting quantitative-based research. And so one of the issues related to measurement includes what's called precision. And precision refers to the exactness of a measure and goes to the sensitivity of the testing instrument, or rather another term that is often used is the resolution of that testing instrument. So some examples include measuring heart rate, and in this picture to the right hand side is an electronic heart rate monitor and is usually provided in whole numbers. If we're using surveys and questionnaires, oftentimes there is a limited set of options or categories, and if the options or categories do not provide enough precision, then more can be added. However, adding too many options or categories to a particular variable in a survey or questionnaire may create redundancies and not make it efficient as a research tool. We begin with, on this slide, with an examination of such scales. And at the most basic level is what's called the nominal scale. And nominal scales are used simply are used in an identification manner. The nominal scale does not actually assign value or an amount, but rather classifies groups or categories or responses. And some examples, as we examined in a previous lecture, is the question of whether people believe that professional athletes make too much money. And the questionnaire only allowed a yes or no response. And in this case, the outcome does not impart any unique value where yes is of greater or lesser value than no. One final point on this example is that the outcome variable here in the answer to the question would be considered a dichotomous variable, as is the categories for sex at birth. And so sex at birth can be assigned or is assigned as male or female, and so there are only two categories. The other definition includes sex at birth variant, which includes three categories: male, female, and intersex. And gender includes three categories: man, woman, and non-binary person. And these are all definitions that have been adopted effective October 1st, 2021 by Statistics Canada. And the key point here is that sex at birth is a dichotomous variable, and here we see sex at birth variant and gender both cannot be defined as dichotomous because there are three categories. The key aspect with the nominal scale is that it has to satisfy certain criteria. The first criteria is mutual exclusivity, and this implies that the selection of an answer for the professional athletes can only be a yes or a no. A single research participant cannot simultaneously select both options, and so there must be one and only one category for each case. Each case in our examples represent a single research participant. It must be exhaustive, and what that means is that a category must exist for every possible score that might be found. And so this doesn't in designing a reliable and valid question for a survey or a questionnaire, if the data are intended to be nominal in nature, there must be categories for all possible responses. And it must be homogeneous. Categories should include cases that can be comparable. So if we go back to our example, we can compare the number of yes responses to the number of no responses. We can compare the number of males to the number of females. Under the first definition, we can compare the number of males to the number of females to the number of intersex, with the definition of sex at birth variant. And you'll see in all four of these examples, all three criteria have been met. Moving up one level is what's called the ordinal scale. And as the term suggests, this is a measurement that is starting to establish some degree of order to the outcomes. And that is a rank order that assigns some level of value to each selection. And so in this particular type of scale, scores will only indicate a position between items and does not indicate any particular magnitude. Some examples include opinion surveys, where some examples of the common selections that are available include agree, strongly agree, or disagree, or strongly disagree. And in this case, the researcher may assign some sort of rank order to the opinion survey. It depends upon the survey, and it certainly depends upon the nature of the question. In this example you see in the photo includes a clinical measurement of muscle strength as illustrated by this therapist and a person suspected of a muscle injury. And so the therapist is using what's called a manual muscle test for strength that doesn't require any sophisticated equipment. And so based upon the therapist's personal experience, they'll grade the level of muscle contraction or muscle strength in a suspected injury from a scale of 5 down to 0, where 0 is defined as no evidence of muscle contractility. And this scale can be expressed as a percent, and these scales usually have a single word verbal descriptor. Sometimes it involves more than one word, but a verbal descriptor that accompanies each level of this very established order, where a grade of 5 is considered normal strength, which in this case the person does not have that injury that would affect function, down to 0, where there's no evidence of muscle contractility. Moving up one scale is the interval scale, and at this point we start to actually describe a quantity. So we use numerical values that will apply a magnitude to the item or the variable that we are quantifying. The interval scale is so defined as having an equal amount separates the scores, hence the term intervals. The interval scale can take on negative numbers, and in this case it doesn't have a true 0. The score of 0 on an interval scale just indicates a location and not an actual magnitude. And a couple of examples here include temperature, and so on the scale of Celsius or Fahrenheit, a temperature of 0 does not mean the absence of temperature. It's just a relative number to quantify a warmer temperature or a colder temperature. Age of years usually is used. An age of 0 indicates birth as a reference point. Income in dollars also indicates a reference point if we consider debt along with that, which is usually described in negative values. And so in this case, 3 examples of variables include temperature, age, and income. Now, if we are interested in measuring temperature, if we're interested in measuring age or income, these and we quantify these, it's very important to understand that they are units. So every quantification must have units. And so Celsius or Fahrenheit for temperature, years in age, and dollars for income. And now in terms of age, this could also be defined in months, weeks, or days. The highest level is the ratio scale. And in a very similar type of approach with the interval scale, these are scores that represent the true amount of the variable that is present. And it's the true amount. In this case, a 0 indicates a absence of that measurement. And so once again here we see some measures that often can be fit under the interval scale definition or the ratio scale definition. So an employee salary in this case of 0 would mean that that employee is not being paid any money. That's a little bit different than income, where a person could be generating a negative net income if they are paying out more than what they're bringing in. And based upon how age is defined, age can fit both interval scale and ratio scale. In the interval scale, if age is considered, if the pre-birth time is considered in age, it would be considered along the interval scale. If we do not consider pre-birth time, then age would be under the ratio category. So when we talk about defining variables, variables in a research project have to be defined very explicitly, because in a very general sense we can see that there is overlap. Some variables of interest can be considered interval, and the same variable can be considered a ratio variable. And once the measurement scale has been developed, then depending upon the research question and the approach, then we would rely on what's called inferential statistics. And to understand inferential statistics, we have to go back to the difference between a population and a sample. So recall that when we talk about quantification, a population will have parameters, a sample will have statistics. The population parameter will most often have to be assumed, and in rare instances can be measured with a very small degree of error. And so, but from a practical research perspective, researchers do not typically have access to the full population and have to rely on direct observation from a sample of research participants taken that represent the population of interest. And so those direct observations are obtained, calculations are performed, and then based upon the sample statistics that are generated, we would then infer conclusions back to the population. And the table here highlights the various symbols identified a little bit earlier in this unit, where Greek symbols are used to indicate the population parameter, and English symbols are used to indicate the sample statistic. And there is a very clear relationship between the population and the sample. So if we begin with an interest in the population, that we know from a realistic perspective that as a researcher we do not have the capability or the resources to perform measurements on the entire population. And so in theory we would randomly select, but there are in practical sense random selection is rarely possible. But nevertheless, a small number of individuals that represent the characteristics of the population are sampled, data are obtained, and so one such statistic that is calculated is the sample mean or an average score on some variable. We would then infer that this sample statistic is representative of the population average or the population mean. And so we perform these mathematical calculations, we generate statistics from a sample of people, and we infer that our direct observations on the sample statistics are in fact reflective of the larger population. And so the conclusion here is that the observations from the sample represents a greater probability of occurrence if we obtain a different sample from the population than what would occur through random chance. And this idea serves as the foundation for inferential statistics. So this ends this lecture of our this part of our Unit 4 unit.